Have you ever wondered what a complex function looks like? Even though real functions have graphs that are easy to visualize, this doesn't seem to be the case for a complex one. There are actually many ways we can visualize these functions. Each of them brings something different to the table, and in this video I will explore them to see if any of them deserves to be called the graph of a complex function. First things first. What is the problem with trying to visualize a complex function the same way we visualize a real one? When we make the graph of a real function, we use two axes. One for the domain, that we're coloring in red. This is where the values of the variable x are. And we use another for the codomain, that we're coloring in blue. This is where the values y of x of the function are. Since we only need one dimension to represent a real number, each of the axes takes one dimension. So the graph as a whole takes up two dimensions, which is perfect to draw on a surface. However, we need two dimensions to represent a complex number, one for the real part and another for the imaginary part. So each axis would take up two dimensions, and the graph as a whole needs four dimensions to be visualized. Unfortunately, we live in a world with only three dimensions, so this straightforward method is not possible. Let's look at an alternative. Here we have on the left the domain axis, and on the right there's the codomain axis. Since these deal with complex numbers, they need to be two-dimensional. What a function does is take points from the domain and maps them to points in the codomain. Let's see this in action with the function f of z equals z to the fifth power plus z cubed. We are using f to take points from the circle to the left into the curve to the right. If we keep the circle fixed but change the function, the curve to the right will also change. Here we have z to the fourth power plus z and z cubed minus z. The idea of the first visualization method is to consider a grid in the domain and looking at what happens after the grid gets mapped. Here we have z squared. The result allows us to understand how a square is deformed as we move it in the domain. But this gets easier to interpret if we add some visual aids. Keeping z squared as our example, let's first get a closer look. To make things less confusing, I'll color in red the lines that are horizontal on the starting grid, and I'll color in blue the vertical ones. So starting from the origin z equals 0, we get mapped to the point f of 0. Taking a step in the red direction, z increases by 1, and we get f of 1. Taking a step in the blue direction, z increases by I, and we get f of I. We could do this with a different starting point. If z equals 1 plus I, then taking steps along the red curve gives us f of I and f of 2 plus I, with z increasing in one direction and decreasing in the other. Similarly, stepping along the blue curve gives us f of 1 and f of 1 plus 2i. This idea of stepping along curves is how you can read these graphs. But of course, this is not without its problems. Let's step back a little bit and now let's walk a little around the graph. As you can see, when we got to minus 2, we got to the same point as when we passed through z equals 2. This is not surprising because we're looking at the function z squared, and the square of 2 equals the square of minus 2. It might not look like a big deal, but this means that if we try to look at something a little bit more complicated than a simple power, then things will get very complicated. Let's take another step back and see what I'm talking about. We're still looking at z squared. Now let's change it to z cubed minus z. If that looks confusing, that is nothing. Check out z to the fifth power plus z squared. It's clear that if we want to tackle more complicated functions, we will need a simpler visualization method than mapping grids. A different approach, called domain coloring, tries to solve the problem of fitting a four-dimensional graph into something understandable by looking for dimensions elsewhere. Instead of spatial dimensions, we will use color dimensions. Every pixel in your screen has a color defined by a precise mixture of red, green, and blue, RGB. These quantities can be thought as free coordinates, meaning that we can arrange all of these colors in a cube. Borrowing some dimensions from this color space will reduce the amount of spatial dimensions needed to convey the information in the graph. But the color dimensions used for domain coloring are normally not red, green, and blue. What's usually used instead is the hue of the color and how bright it is. To understand how this is done, we must recall that all complex numbers can be written in a polar form, where instead of the real and imaginary parts, the number is described by its absolute value and its angle theta. What domain coloring does is encode the angle as the hue and the absolute value as the brightness. Visually, it looks something like this. Here, the arrow is pointing to a complex number, and if we extend it to the disk, we get the color representing that value. So as the arrow spins, the angle of the complex number changes, and together with it, the hue representing it. If on the other hand the absolute value changes, the color keeps its hue but changes brightness. Normally, smaller absolute values are represented by darker colors, and larger absolute values are represented by brighter colors. So we know the function is close to 0 if the color is close to black, and we know the function is big if the color is close to white. A downside is that because of the way colors work, if the brightness is either too low or too high, the hue becomes harder to tell. A different way of using brightness to denote absolute value is adding contour lines. If you ever used a map that had indications of elevation, those lines that tell you how high or low a place is are contour lines. The idea is to do the same, but for absolute values instead of height. Now, that's enough talk. Let's see how domain coloring works in practice. We'll start with the function z divided by z squared plus 1. That's a pretty picture, but what is this? As the name implies, we're looking at the domain of the function. In particular, the real and imaginary axes are going through here. So the points in the screen have the coordinates of z. What about the colors? These represent the value of the function. Different hues represent different angles. So reds and blues have different angles. Same for yellows and greens. In particular, if we follow the real line, we see that a pure red corresponds to a positive real number, while cyan is a negative real number. And this yellowish green is a number with no real part and a positive imaginary part. Similarly, purple is a number with no real part and a negative imaginary part. We can also see the root of the function in black at z equals 0, as well as the 2 points where the function blows up in white at z equals I and z equals minus I. As I said, another way of exploring the brightness is with contour lines. In particular, these contour lines I'm using have a bit of bleeding. The blurrier the line, the slower the absolute value is changing. We can still see the root of the function and the points where we have blowups, because the contours bunch up around those points. Let us move on and take a look at z square. Here we can see explicitly that the square of z equals the square of minus z, because if we rotate the figure by 180 degrees around the origin, we'd get the same exact image. Another interesting example is the exponential function. The angle here repeats periodically if we move up. This is because the angle of exponential of z is just the imaginary part of z. So moving along the imaginary axis is like moving around a circle. Walking along the real axis, on the other hand, we see equally spaced contour lines. This is because the absolute value of exponential of z is the exponential of the real part of z, and I'm using a log scale for the contours. This, however, shows a weakness of drawing unlabeled contours like these. If we were to go back to encoding the absolute value as brightness, we would get a completely different picture that better shows how exponential of z grows. But you also lose a lot of the precision you get with contours. One possible solution is to combine both ideas. Let us leave exponential of z and move to a different function. This is z to the fifth power plus z squared. We can see here its roots and the fact that it diverges when the absolute value becomes very large. The way it diverges gets clearer if we add contour lines. We can now see that it becomes very homogeneous as we get farther from the origin. Moving on to something more complicated, this is the tangent of z. Here the contours show us that the absolute value changes mostly close to the real axis. And the brightness lets us tell apart what are roots and what are blowups. The graph also shows us that the tangent of z converges when the imaginary part of z goes to infinity or to minus infinity. Namely, it converges to I and minus I. Something similar happens when we look at z minus 4i divided by z plus 4i, with its root at 4i and a blowup at minus 4i. Let us take a step back and think about what we're doing for a bit. I've shown you two different ways that we can make a graph of a complex function, and in a sense they are opposite to each other. When we mapped grids, we were registering z at f of z. That is, the information is which values are carried to a given point by a function f. The main coloring, on the other hand, registers f of z at z. The information is the value that f takes at a given point. Now, we have seen these methods are not perfect. Let me highlight some problems and see what we can improve. The main issue with mapping grids is that the lines crossing each other get very confusing. This is an inevitable byproduct of registering z instead of f of z. On the other hand, even using only two color dimensions, the main coloring packs way too much information in colors. One possible improvement is that since we can spare a third spatial dimension, then we only really need to use one color dimension. If we do this right, we can keep the general spirit of domain coloring, but making the colors easier to interpret. Let's see what happens if we use the z-coordinate for the absolute value and keep using the hue for the angle. Let's start with something very simple. F of z equals z. If we were to add axes to this, they'll look like this. But I'll leave them out so that we can just move around and explore the shapes. We can see, as expected, the absolute value growing linearly as we move away from the origin. And spinning the surface, we see the different hues representing the different angles. If we look from the top, we'll see something close to the usual domain coloring. Let's move on to z squared. We can see now that adding a third dimension allows us to have a much more precise idea of the absolute value than we ever could with domain coloring, even using contours. Let's take a look at z to the fifth power plus z squared. It's clear now that the function is much steeper than z squared, which also wasn't obvious with just domain coloring. Finally, let's look at an example where there is a blowup, z minus I divided by z plus I. We can clearly see the blowup at z equals minus I, as well as the root at z equals I. It shows up like a kink in the surface. Now I want to move to a final question. Are any of these visualizations the graph of a function? First, what is the technical definition of a graph? Well, the graph of a real function is actually defined by this: a set of points, x and f of x, for x spanning the whole real line. But how do we translate this into something more tangible? Suppose we make the plot of a function. For every horizontal coordinate x, we have a corresponding point with vertical coordinate f of x. So the point in the curve is x and f of x. But this means that the graph of the function is the curve, but thought of as a set. For a complex function, the graph is defined in a similar way. But we must take into account that both the variable and the function have a real and an imaginary part. So the graph will be the points x, y, representing the parts of the complex variable z, and u of x and y, b of x and y, representing the parts of the function value f of z. So for a real function, the graph is an object in 2 dimensions, having one parameter x. The result is a curve in the plane. A complex function, on the other hand, has a graph that is 4-dimensional, but has 2 parameters, x and y, and this results in a surface in some 4-dimensional space. So if you want to truly see the graph of a complex function, we need a way to see a surface in 4 dimensions. This is actually a very common problem, and the main tool for that is called projection. This is how we are able to see things like the Klein bottle or the boy surface. Projection is actually very simple. It can be thought of as rotating and translating an object and then just getting rid of some of the coordinates. Actually, the grid mappings we started with are projections of the graph, where we got rid of the first 2 coordinates. Let us instead get rid of the last one. So we'll use the z-coordinate for the real part of the function. This is z squared. We can now see an upwards parabola if we move along the real line, and a downwards one if we move along the imaginary one. This is z cubed. And this is z minus I divided by z plus I. Comparing this to what we had using the absolute value as the vertical coordinate, we see a completely different way that the blowup looks like. We can now see that we can reach the blowup in 2 different ways, with a positive real part or with a negative real part, depending on the side that we choose. This fact is only registered in the colors of the previous plot, so it's very easy to miss it. Finally, we can add back the 4th dimension that we dropped by coloring the projection. We could either color it according to the imaginary part of the function or according to the angle of the function, which is what I'm doing so that we have an easier time comparing with the previous plots. Let's try, for example, the tangent of z. Try recalling and comparing it with the domain coloring that we had earlier. And let's now just finish with z squared. I hope you found this interesting, and thanks for watching.